There is one more way in which you can describe the strength of an association between two quantitative variables. So actually this would have fit rather nicely after the story on the correlation coefficient, but it's a bit more challenging, so we have saved it for last. It's all about explaining variation. The story for this last part goes as follows. Personnel at Casa de Salsa were required to dance while serving customers. This way they could contribute to the brand's cheerful image. However, dancing is a tricky thing to do when you're carrying food around. Cervantes had heard many stories about overconfident waiters and waitresses who, while twirling around on their heels or waving their arms to the beat, dropped a whole plate of tapas in a customer's lap. To see what might be the problem, Cervantes drew a small sample of waiters. She observed for each individual how many plates they usually carried at the same time and how many dishes they actually accidentally dropped during their work shift. Here are the outcomes. Voila. So you have here all the individual scores. There are now just 7 participants, so it gets increasingly unrepresentative, but it's all just to ease up the calculations, so to say. You have a scatter plot of how these two variables are related. You have the regression line already drawn through the scatter plot, and if we did the calculations that we have learned about again on this data set, then we would find again a pretty strong correlation of 0.48, and we would find a very straightforward regression equation of the form 0 plus 1x. Y hat is 0 plus 1x. So I'm assuming that we now know how to deal with the calculation of the correlation and those regression coefficients, which lets us talk about explaining variation. What is variation actually? Variation has to do with, as the name implies, how much people differ from one another. Specifically, what we could do is we could see how far people differ from the mean. It becomes clear if you look at the scatter plot that some personnel, some waiters, caused far more accidents than others. You have a few who didn't drop any plates at all, didn't drop any dishes at the bottom of the plot, and there was one who caused no less than 8 accidents during their work shift. So there's a lot of deviations from the mean, and we can calculate all of those. Here they are. Again, the bar above the y is a bit unsuccessful, huh? So what we're calculating is how much each individual score deviates from the mean, which I've also visualized in the scatter plot using that horizontal bar. And you could say, well, this is the first step towards a standard deviation. Now, this is also what we do when we want to figure out the average deviation from the mean. We would first need to see how far does every individual deviate, and then we can try to make an average out of that. I hope that looks a bit familiar. So we do 1 minus 3, 3 was the mean for the first person, 1 minus 3 is minus 2, that's how far they were below the mean in terms of how many accidents they caused. And we do the same thing for all other subjects as well. What should we do then when we want to calculate a standard deviation? Well, the thing is, if you want to make an average, then we normally add up the deviations of sorts, huh? But if you add them up just like that, they will always cancel out. Some individuals are above the mean, others are below, and the net result will always be that the average person deviates not from the mean at all. That's the definition of the mean, basically. Yeah? The solution is to square the deviations before you add them up. And that is when you obtain what is known as the sum of squares. In this series, we refer to it as the total sum of squares, the sum of squares total. It is sometimes also called the total variation in the data, although this term is a bit more common in Dutch than it is in English. This total sum of squares, the total sum of squared deviations. Yeah, so that takes a minute. You would have to square all those deviations that you just determined and add them all up. Feel free to come along on your calculator. So minus 2 being 4, meaning minus 2 being 4 if you square it, und so weiter. And this leads us to a total sum of squares of 52. 52 is the total variation in the data. So this is a kind of total package of how everybody deviates from the mean. The 52 on its own does not have much meaning, as it's just a package of square deviations. Pretty much a mathematical abstract, right? But you can imagine that if participants are more similar, then this sum of squares will not be that large. If everybody is pretty close to the mean, then the total sum of squares may not be very much. It of course gets bigger as you add in more participants, but if the same set of 7 participants had been more similar, then the total sum of squares would have been smaller, and if they had differed more from the mean overall, then the total sum of squares would have been larger than the 52 we have right now. If we wanted to carry on towards a standard deviation, then we would once again average out this thing. So we would divide it by n minus 1 to get what is known as the variance. And then we could take the square root to get the standard deviation. I'm just skimming this slightly, as we can also do a couple of things with sums of squares. So we don't go on to standard deviations right now. We just stick with this.